All right, let's um, let's look at inducing motion. Uh-oh. Uh-oh, I got problems here. Uh-oh. It's gonna be okay. I think it'll be okay. Hang on here. Inducing, there we go. Inducing motion with electromagnetism. And we're going to start with a little bit of background theory first, and then we'll get to the motion. Okay, now we have to represent in 2D stuff that happens in 3D. Okay, so I'm going to draw a little picture of our setup, and then I'm going to show how we're going to represent it in 2D space a little bit better. Okay, so imagine you got a bar magnet oriented like this. Okay, if you want, here's my Y plane. Okay, my X plane is like this, and my Z plane, if you want, is in and out. Okay, so Y up, X right, Z in and out. So if you're talking about, you know, your kind of 3D Cartesian scenario, that's what we've got going on here. All right, so if we put, let's say, the North Pole up and the South Pole down on this U-shaped horseshoe magnet, then we know from experience that if we were to put a compass in here, we would create a magnetic field within here that goes like this. Okay? And we don't really care that much about what's going on out here, but this is kind of the scenario. Now we're looking from the side on, and what we're going to do is we're going to pass in the Z plane a piece of wire across this field. Okay? Okay, so it crosses through. Hopefully that makes sense. So in other words, you know, we're kind of looking from this perspective, and we're saying that the wire is aiming kind of away from us. We're seeing this from the side. Okay? So if we have a wire like this, what we're going to say is charge can be passed through this wire. All right, so we can hook it up to, you know, a circuit with a battery. We can have charge or current flowing through. We're going to say our current flows this way. So we call that I. Now in traditional physics, we're going to call I positives. Okay, I'm going to say like positives flow through here. We know in reality the positives can't move. All right. It's actually electrons moving in here, but all the physics that kind of look at this were invented before people knew about electrons, and they just kind of, actually it was Ben Franklin, kind of placed a guess on, he rubbed silk with, he rubbed glass with silk, and sort of said, you're positive and you're negative. But he actually guessed wrong. So what he was calling positive was actually the collection of electrons, right? Once those two things got charged up, and here we are, you know, 200 or 300 years later, with our positives and minuses backwards, right? So really, it should be negative charge flowing this way, but none of our right-hand rules will work with that scenario. So we say current flows from positive to negative, and we assume it's positive charges flowing, even though we know that's not true. Okay? Now, what will happen is when you juice this up, a force will be induced. This wire will tend to move. And we want to know what are the physics that, you know, dictate, or how do we remember which way this wire will tend to move? And the reason why, okay, just a little more background actually, is you can place a compass nearby a current carrying wire, and you will find that a magnetic field exists cycling around this wire. Okay, so your compasses will be caught up and point in this kind of like circular direction, okay, around here. And we have a rule to dictate which way this field cycles. And I think it was Michael Faraday who said, imagine that your compass is like a flag, and this is like a wind, right? You place your flag in the wind anywhere, and it's going to point in the direction the wind's blowing, okay? So this is what you get, and you use your right-hand rule where you point your thumb in the direction of current along this wire, okay? And then your hands, your fingers, are going to curl around. This is always hard for me to draw. Your fingers curl around. Yeah, that's right. Salad fingers. Okay? And so you've got your wire going like this, kind of through the hand as if you're grabbing it. I'll put another little video up of me actually doing this so it makes more sense. Okay, and then you get your field pointing around like your fingers are going. Okay, I'm sure you all know the right hand rule. Okay, not very great, but close enough. So when this charge flows and you get that coiled magnetic field, well, it's going to interact with this horseshoe magnetic field, right? And it's going to cause this wire to move, all right? So we're going to look at the why. So this is what we're going to do. We're going to represent a magnetic field in an area, okay? And we're going to imagine that we could stick our head like right inside here, right? So we're going to poke our head in here, and we're going to look from north to south. So the magnetic field is passing like, if this is our head, here it is. Make you look real good. There you are, okay? There's your head. You've stuck your head inside here. This is a huge magnet. You've stuck your head inside. So you're seeing the magnetic field pass through your head. So in other words, all right, in this scenario, what we're saying here is that north is on this side, south is on this side, and this is three-dimensional, right? Or even better, north is here, and south is like back behind here, okay? So what we're going to see, right, is we're going to see the magnetic field, but we're going to see it like end on, and we're going to see it like going away from us. So there's a way to draw this that's sort of like agreed upon, and it is like using little X's. So if the field is passing away from you, you would draw that as, you draw X's. And a great way to remember that is, let's say you are an archer, okay, and you shoot an arrow, right? You shoot an arrow. And if you shoot the arrow and you look at it, as it's flying away, you're going to see the feathers of the arrow, and they're going to look like a cross, okay? So away from me looks like crosses. And towards me looks like what you would see if you saw the front of the arrow coming towards you, which would be little dots. Okay? So to draw a field moving away from you, you draw X's, and toward you draw dots. Okay? Remember, what this is you sticking your head in the field and either looking towards south or looking towards north, right? Here you're looking towards south, south's back behind, north is on behind your head, and now you're looking up towards north here, and the field's coming towards you. Okay? And then what we're going to say is, well, what happens if we just take a proton, say, or some kind of positively charged particle, and we inject it into this field at high velocity? So here it is. Here's our proton or charged particle, and we zip it in here at high velocity. Well, it turns out that the reason these wires exhibit magnetic fields when charge is passing through them is because that any moving charge out there moving through space creates a magnetic field around itself, all right? So really, these have magnetism because they're filled with a whole bunch of moving charges that travel along, and every individual charge makes its own magnetic field. Since they're all moving in the same direction, those magnetic fields that these charges are exerting, right, build up. So now we're stepping aside and we're saying, I'm shooting into this magnetic field a high velocity positive charge, say, okay? And what will happen is once this gets into the field, it's going to curve. I'm going to do this. Okay? And if I injected it, say, down here, this velocity, okay, here's its velocity moving in, okay, it's going to bend this way, okay? And actually, you can probably see that it's the same way if you just imagine like taking this whole thing and moving it around. And same over here, right? It's going to tend to move over this way, okay? The reason why is the interaction between the electromagnetic field and the permanent magnetic field. So how do I remember which way it tends to turn? And we're going to introduce one more right-hand rule to show that. So you're going to take your hand, and you're going to point your fingers in the direction of the magnetic field. So in this case, since we're looking at it, okay, my fingers are going to point directly away from me. So there they are. There's your fingers. Okay. Your thumb, you're going to stick out like that, and your thumb is going to line up with the velocity, the direction the velocity is going. Okay? So I'm drawing this hand upward, but really what you should imagine, and if you take your hand and put it out in front of your face, and you line your fingers up directly into the page, and you point your thumb to the right, what you should have in front of you is your hand with your palm up. Okay? Your hand with the palm up. Okay, I could not for the life of me find a picture of someone with their palm away, and then it dawned on me, just use your own palm. So there it is, okay? So this is what your hand should look like from your point of view. Your fingertips pointing towards those X's, right? Because it's representing the magnetic field as pointing away from you. And I think I could probably actually just label the hand here. Or possibly not. Can I label the hand? There we go. Okay. So pointing away, we have B, representing the magnetic field. Pointing to the right, okay, we have V, representing the velocity of positive particles. And then my palm is going to point up towards the sky, which is the direction I showed that in any of these scenarios, and I'll move this in a second so you can see a bit better. Oh no, I'm not going to do that because it's going to ruin my picture. But pointing up towards the sky is the magnetic force that that particle will feel. So up wherever my palm is pointing, we call that FB. Okay, the force caused by the interaction of the magnetic field created by the moving charge and the existing magnetic field. Okay, so there it is. So put your hand out in front of you. This is a right hand rule. Okay, the reason being is because your fingertips are pointing in the direction of the magnetic field, which in this case is away. Thumb in the direction of the velocity of the particle. So if I look at this particle over here on the right-hand side, or this one over here on the right-hand side, you can realize that your hand's going to have to like flip over, right, to orient itself correctly, to keep the velocity going the same way and keep your fingers pointed away from you. And the force on the moving charge would then be down. Okay? Does that make sense? Now, if we continue to think about this, what happens if we, I'm going to move this down, if we now have to deal with magnetic field coming out of the page, all right? So if we were to say have, I'm just going to erase my sad attempt at drawing a hand. If we were to say have the charged particle be positive and come in this way, okay? So now my fingers are supposed to point in the direction of the magnetic field, but now it's aiming towards me. So in my picture, it's as if I'm now looking up towards the north, and the particles are coming in from the side, okay? Well, in this scenario, we flip the magnetic field over. We've got to flip our hand over so our fingers point towards our face. Do we need a picture of that? Okay, it turns out it's really, really hard to aim your hand at your face and take a picture because your fingers are practically on your nose when you do that. All right, but anyway, the point is that now, okay, B, the magnetic field, is pointing towards me. Ah, for goodness, come on. I don't know what's happening. There. For goodness sake. Okay, so B, the magnetic field, right? It's like little arrows aiming at us, so that's what's represented here. Velocity of this particle is to the right. So we would expect then that the force on the object would be down. All right, so going back to the picture then, right here, we would say the force on this object would be in this direction. All right? So this is how your right hand rule works. Essentially, you just lay your hand flat out, thumb in direction of velocity, fingertips in direction of magnetic field, and force will be shown by your palm. Now, you might say, well, what if a negatively charged particle comes in here? So for that scenario, you're going to do the exact same thing you did with your hand, right? So in this case, you're going to point your thumb to the left. You're going to point your fingers towards you, right? So that's kind of hard to do. You're going to have to like contort your right hand. And it's going to tell you that this thing will aim up, except because it's negative, you flip the direction of the force. That's all. So instead of being aimed up, this curls like that, okay? And the positive charge would curl like that, as shown by where your hands are. So that's the difference, okay? You still use a right-hand rule for negative. You just realize that the thing that changed about this is the direction that the force would act in. Yeah, you just realize that your right-hand rule is based on a positive charge, and if it switches to negative, you just flip the direction of the force from palm to back of hand. Okay, so now where we wanted to get with all of this is, can we use this to discuss and discover what happens when you have a wire suspended through a magnetic field like we had way back here, and you start to pass current through it? Well, which way does the force tend to act on that object? So I'm going to actually make it come right through from left to right like this. Okay, and we're going to say that this side's the positive and this side's the negative. So in that case, current is traveling this way. All right, and if we realize that what current is a bunch of charges moving in this direction, then we can understand that really it's the same scenario that we just had, except now we're going to aim our fingertips into the page, our thumb is going to be to the right, and we should expect to have then an upward force acting on this wire along its length. All right? Now, what plays into how much force there's going to be, how much will it be, are a few things. One will be the current. How much current is there? Lots or a little? The second is, how strong is that magnetic field? Is it big or small? Okay. Current, remember, we measure in amps. B, magnetic field strength, we measure in Teslas. And the third thing we need to worry about is how much of this wire is exposed to the field. So L, the length of wire in the field. And there's one last thing, okay? No, B is measured in Teslas all the time, okay? Orientation of wire to field, okay? So it turns out that you only get force when the charges are moving perpendicularly or at a right angle to the field. So in other words, if I were to pass a wire this way through the field and say have the current now coming towards me, all right? In that case, the field and the direction of travel of charge are in the same direction. We would find no force in this scenario, okay? So it's only perpendicular to the field that exhibits some kind of force, all right? So when you're using your right-hand rule, what you're trying to represent is this perpendicular nature, right? Field in one plane, velocity in another plane, force in the third plane. So it's 3D represented on 2D, okay? And what you get from all of this is you get a little formula that has been worked out. And that is that the force is equal to B, the magnetic field strength in Teslas, times I, the current strength, the current strength in amps, times L, the length in meters, and then what's often tacked onto the end is sine theta, okay? The reason being is because if sine theta equals 0, in other words, we're in the same plane as the field, we get no charge. What's the sine of 0? It's 0. So we want it oriented at 90 degrees to the field to get max force on here, because sine of 90 equals 1. So if we're at 90 degrees, it's essentially like tacking a 1 on here. If we're at 0 degrees, it's like tacking a 0 on here, all right? And then some value between 0 and 90, all right, is going to show that you have an increasing or a decreasing overall amount of force. I wouldn't really sweat this. You're pretty much only going to get questions, at least at this level, where it's oriented perpendicularly. But later when you talk about, say, generating electricity with, say, moving wires, or you want to talk about an electric motor, how you can make this into an electric motor, okay, then the sign does become important. So I just want to, before we break from this, I want you to imagine something. Imagine this is a perfectly cylindrical wire. And imagine that we just rest this on metal rails, okay? So we've got to rest it on metal rails, and it's free to move on these metal rails, okay? And these are representing these wires attached to these rails. And we're going to put a positive and a negative end on here, okay? So we're going to have that current flowing around like this, okay? So if this is free to move, once we start up, if there's a switch on here, we flick the switch or we attach the battery, this will roll away at high speed in the upward direction because there's a force all the way along its entire length based on the flow of charge through here. If we flip the direction, we can make it like roll back towards us, okay? So we can actually make this like roll one way and then the other. So what we're doing is we're causing the interaction between electricity and magnetism to create motion. This is the basis of really any electric motor or servo or anything along these lines, really actuator, linear actuator, and so on, that is driven by electricity. It's the interaction between electricity and magnetism at its heart that allows motion from moving electricity. You think of all the things in your house with an electric motor that did not really exist before this physics was found out, and it'd be a very different household, right? No, say, blender, no garage door opener, no, what else? I don't know. Lawnmower? Well, I guess if you have an electric lawnmower, sure. Just anything with an electric motor. Toast? No, not toast. Toast doesn't have an electric. Toaster doesn't have an electric motor. But anything, like any really like home appliance that spins or mixes, right? Electric motors are just in them. All your electric power tools, right? You need to understand. I mean, I guess you don't need as a consumer to understand. But if you want to build these things and make better ones, you got to understand the relationships between magnetism and moving charge. So I just want to solve one problem. You might see a problem like this on your final exam. It might say, a wire is 4 meters long and rests at 90 degrees to a magnetic field that is 5 times 10 to the negative 3 Teslas in strength. Okay, and again, I'm not going to define the Tesla right now. That's for later, but just use it as is. A current of 4 amps is passed. What FB would you expect? Okay, so what force would you expect? And let's just quickly draw this picture and solve. It's pretty easy, I think. Okay, so we have this. Let's make it like this. Okay. Let's put our wire like this, 90 degrees to the field. Let's say our current flows that way. So the first thing is, if current is flowing that way, which way will the force act? Get your right hand out. You got to point your fingers towards your face. You got to point your thumb down, and you're going to see that force would be to the left. So the direction of motion on this wire would tend to be to the left. Okay? And to figure out what that force would be, it's just simply BIL. So we say B was 5 times 10 to the negative 3 Teslas. Current I was 4 amps. The length of the wire was, I think, did I say 4 meters? Yeah, okay, 4 meters. And it's at 90 degrees, so we can tack the sign 90 on there, but really, that's just like multiplying by 1. So this is the maximum you would have. If you started to like rotate this wire away from you, you'd find that the FB would decrease sinusoidally, actually, but we don't need to get into that. And yeah, let's do some calculating here. So 5 times 4 is 20, times 4 is 80, right? So 80 times 10 to the negative 3, or 8 times 10 to the negative 4. I think. Whoops. My bad. Math's hard. There we go. Okay. What units is this? This is in newtons. Okay, that does it. We're done.